Welcome to this revised lecture on stochastic processes. We start out by recapping some of the models we saw last time. White noise models, independent random variables, not too interesting in themselves, but they are essential for building more advanced models. A random walk, cumulatively adding white noise, not a stationary process, but again, it plays an important role in practical model building. And lastly, an autoregressive model of order 1. It has a dependence on previous values, but not as strong as a random walk, and it's a very useful class of models. We look at these models and add some details, and then we add more tools to our toolbox later. And a keyword in this connection is ARIMA models, autoregressive integrated moving average models. So white noise, independent components W1 up to Wn, identical distributed, zero mean and variance sigma squared. So they are it's a stationary process, very well behaved, and I can simulate data simply by generating normal independent normal variates, and I can create a time plot of data and a plot of the autocorrelation function. 95% or more so of the autocorrelations are within the blue band, so this suggests that that this is indeed a white noise process, which is of course true. This is how we generated it. A random walk is obtained by saying what happens today is what happens yesterday plus a random shock from today. And if we backtrack this, then we find that what happens today is what happened 2 days ago plus the shock from yesterday plus the shock from today. And if we trace that back, we end up saying that the measurements of the data we have today is simply the sum of the shocks from day 1 up to day t. It has a constant mean 0, but the variance depends on t, so the process cannot be stationary. And you get the same, the autocovariance function also depends on t, and so on. If I simulate data, then I will see that the autocorrelation function decreases, but it does so very, very slowly. It appears that there is a linear trend in these data, but this is really an artifact because it is it's not a trend, it's just, what can we say, a stochastic trend, a random trend, a slowly varying component. And it's quite common to call this a stochastic trend. Now, if the coallogram shows a significant autocorrelation at like 1, this means that observations are correlated. What happens today looks like what happened yesterday. And a classical model is an AR1 model. XT, what happens today, is a scaled version of what happened yesterday plus a random shock from today. and alpha is the parameter which needs to be estimated from data. And we notice that if alpha is 0, then an AR1 model is really a white noise process, and if alpha is 1, the process is a random walk. And the process is stationary if and only if alpha lies between -1 and 1. And last time we saw the mean function, the variance function, the autocovariance function, and the autocorrelation function. I simulate data, and a very convenient tool in this connection is the function called arima.sim, and I can simulate data and plot them alongside with the estimated autocorrelation function, and also the theoretical autocorrelation function, the red dots. There are many functions for fitting AR1 models in R, and the one we use is the one from the library called forecast, and in there is a function called arima with a capital A, and this function is different from the arima function with lowercase a that is in the stats package that is in base R. But we're going to use this for throughout this lecture. It's a somewhat more modern version of the basic arima function. In a moment, I'll get to what this order specification means, but for now, this is an autoregressive process of order 1. The alpha parameter is estimated to 0.689, the mean to 0.207, and the corresponding standard errors, and I can get a 95% confidence interval for the parameters using the confident function. Now, in practice, data do not necessarily have mean 0, but the way that we formulated the model, it assumed the mean to be 0. So what we do in practice, and you don't need to worry about that because software will do it for you, but that is that we simply replace xt with xt minus the average x bar. So the model we're actually looking at is a model down here where we can say we have centered the data by subtracting the average. So this also means that if I want to predict xt from xt minus 1, and I look at the model up here, then this will be my prediction, and I then just rearrange so the predicted value at time t is the average plus alpha times the difference between xt minus 1 and the average. Now, residuals are used for checking if a model is a good one, an adequate one, and we just looked at how to form the residual, the fitted values before, called x hat. So if I look at the observed data minus the predicted data, then I get the residuals, and they should, if the model is adequate, behave like white noise terms like the WTs. Mean 0, constant variance, no serial correlation, and no clear pattern. And if the residuals do not look like white noise, then there is some structure in the data that we have not accounted for in our model. So, what we can do is that we can take the fitted model from before and take out the residuals and plot these. This is really, what I do here is really a dumb way of taking out the residuals. Sorry about that. I should do like this. Apologies. But I can make a time plot of the residuals and a plot of the autocorrelation function, and this really suggests that the residuals is indeed a white noise process. The autocorrelation at lag 0 is 1, and afterwards it drops very rapidly to 0. Now there is a function in the forecast package called check residuals, and it actually does this for us, and it does some more. It creates a time plot of the residuals, it creates the autocorrelation plot, and then it produces also a test for if the autocorrelation is significantly different from 0. And the residual plot should look like random noise, no pattern. The autocorrelation should lie between plus minus 2 over divided by square root n, because it is the standard deviation. And if the p-value is large for the test, this suggests that there is no clear autocorrelation. And what we can see here, nothing to worry about, and the p-value is certainly above 0.05. So it looks good for the simulated data set. Not surprising, we generated data ourselves and we checked that the data set fits, has a structure we used to generate from. Now, perhaps now is a good time for a small break. Very often we find that data are not stationary, do not look like stationary process. And then a very classical technique is to consider the time series of differences and see if that series is stationary. So instead of modeling xt, we model the differences xt minus 1. So we simply compute these differences and analyze these as our data. So if xt consists all in all of n observations, then when we look at the differences, there are n minus 1 observations. It's common to use what's called the difference operator in connection with time series. This triangle is called nabla. It's not a Greek letter, but it looks like a delta flipped 180 degrees. I don't know who invented the symbol, but it's not a Greek letter. But it is a useful mathematical operation in its simplicity. So the difference operator applied to xt is by definition xt minus 1. So if I difference data twice, I end up with xt minus 2, xt minus 1 plus xt minus 2. Sorry about that. If a time series is not stationary, but it becomes stationary if we difference it once, then we say that it is an integrated time series of order 1. And if we need to difference it twice to obtain stationarity, then we say it's integrated of order 2. Most often we need to difference, either not difference it at all or difference once, occasionally twice, but having to difference at more times is very, very rare. So if I look at a specific example, random walk, xt is xt minus 1 plus wt, then by definition, the difference operator applied to these data is the white noise sequence. And I can see that here. I get my original data. It looks like there is a trend, but this is really an artifact. And the autocorrelation function goes down, but very, very slowly. But if I look at the differences, things look very, very stationary. Actually, we can use the function check residuals again on data. And it provides at the test, and it says, well, look, the p-value is pretty much 0, saying, well, these this is not a white noise sequence. But if I look at the residuals, then I get a p-value which is certainly above 5%, saying, so this is fine to assume this to be a white noise sequence. So that's a neat diagnostic tool. Now let's look at a real data set. The exchange rate from British pound to New Zealand dollars. If I look at the data, I seem that I have taken out one thing too many from the slides. I'm going to take a break here, and then we will restart the video again. Sorry about that.